Welcome, data architects and AI engineers. Today, we are diving deep into Snowflake Cortex's semantic retrieval capabilities, specifically focusing on the vector inner product function. Let's get started. Before we can understand how to compare vectors, we must establish what they are. In the era of generative AI, we deal with massive amounts of unstructured data, like customer support logs or product reviews. An embedding is simply a mathematical reduction of this high-dimensional text into a dense array of floating-point numbers, a vector. Why do we do this? Because traditional keyword search is brittle. If a user searches for laptop but your database says notebook computer, a keyword search fails. However, modern neural networks place semantically similar concepts close to each other in a geometric space. By converting text to the Snowflake vector data type, we enable our database to understand semantic meaning. But having the vectors is only half the battle. To perform a retrieval operation like finding the most relevant documents for a user's prompt, we need a highly optimized mathematical way to measure the distance between these vectors. Looking at this conceptual flowchart, we see the journey of data. On the far left, unstructured text enters the system. We pass it through a Snowflake Cortex embedding model, which outputs a dense number array R vector. This vector represents the exact semantic location of the text. The critical node is in the center, similarity measurement. We must calculate the geometric distance between the user's search vector and the vectors stored in our database. The mathematical outcome of this measurement directly drives the accuracy of the semantic search results on the right. Today, we focus precisely on that measurement engine. Let's formally define our core function. Vector inner product is a specialized, highly optimized mathematical function built natively into Snowflake to measure the similarity between two vectors. In linear algebra, this is also known as the dot product or scalar product. The function essentially multiplies the corresponding dimensions of two vectors and sums them up. Why is this useful? Because the resulting numerical value represents the combined direction of the two vectors. If two vectors point in the exact same semantic direction, meaning the text concepts are highly related, the inner product will be a larger number. Conversely, dissimilar concepts will yield a much lower or negative number. Implementing this is incredibly straightforward. You simply call vector inner product in your SQL statement, passing in your two vector columns or literals. It quickly processes the arrays and returns a single real value representing their similarity score. This diagram illustrates the function's execution path. We have two distinct inputs, vector A, representing the embedded user query, and vector B, representing a single embedded record from our database. Both are injected into the vector inner product compute node. The engine performs rapid dot product mathematics across hundreds of dimensions simultaneously. It outputs a single real value score. The branching logic below shows how we interpret the score. A larger positive value indicates high similarity, meaning the texts are conceptually related, while a smaller value dictates low similarity. As senior data engineers, we must understand the nuance of the math we deploy. How does inner product differ from other metrics like cosine similarity or L2 distance? The key differentiator is magnitude. While cosine similarity purely measures the angle between two vectors, the inner product measures both the angle and the magnitude, or length, of the vectors. If your vectors are not normalized, a longer vector will inherently produce a higher inner product, which might skew search results. However, most modern embedding models, like Snowflake Arctic, output normalized vectors. When vectors are normalized to a length of 1, the inner product becomes mathematically equivalent to cosine similarity. Why does this matter? Because calculating the inner product requires fewer CPU cycles. Furthermore, Snowflake has aggressively optimized these functions at the hardware level. This optimization brings incredible speed, but introduces a tiny margin of floating point error, up to 1 × 10 to the power of -4, which is entirely negligible for semantic ranking. Let's compare vector states using this block diagram. In the top block for unnormalized vectors, using inner product evaluates both angle and magnitude, which can potentially skew your ranking if document lengths vary wildly. Now, focus on the bottom block for normalized vectors. When the vector length equals 1, the inner product becomes mathematically identical to cosine similarity in terms of ranking order. However, as shown by the bottom execution path, the inner product achieves this result with significantly faster compute. For large-scale AI applications, this architectural choice saves time and resources. Let's talk about implementation and syntax. First and foremost, you must utilize Snowflake's native vector data type. When creating your tables, you define the column as vector, specifying the base data type, typically float, and the exact number of dimensions, such as 768 or 1024. To execute the function, you simply write select vector inner product, passing your two vector columns. If you are prototyping or testing, you can pass literal arrays directly into the query, but you must explicitly cast them using the double colon syntax, like bracket 1, 2, 3 bracket cast to vector, float, 3. It is absolutely critical to remember that vector mathematics requires symmetry. If you attempt to calculate the inner product of a 768-dimensional vector from one model with a 1024-dimensional vector from another model, the Snowflake engine will throw a hard error. The dimensional lengths must match perfectly. This sequence diagram shows the strict validation process within the Snowflake engine. The SQL developer issues the select statement invoking vector inner product. The engine immediately checks the metadata of both vectors. If the dimensions match exactly, the engine proceeds with the dot product calculation and returns the float value, representing the similarity. However, if there is a dimensional mismatch, say comparing an Arctic model vector to a Voyage model vector, the engine aborts the calculation and throws an execution error, protecting your application from invalid mathematical comparisons. As architects, we must strictly govern our cloud costs. There is a massive financial distinction you must understand when building AI pipelines in Snowflake. Generating the actual embeddings using Cortex LLM functions incurs specific token-based compute costs. You pay for the text you embed. However, the vector similarity functions themselves, including vector inner product, do not incur any token-based LLM costs. They are mathematically pure functions executed natively by the Snowflake SQL engine. This means the cost of calculating the similarity between millions of records is simply the standard cost of running your virtual warehouse. Because it leverages Snowflake's massively parallel processing, MPP, architecture, it can calculate the inner product of millions of vector pairs across a distributed cluster in a matter of seconds, making real-time, large-scale semantic search highly cost-effective. Follow the billing logic in this flowchart. On the top left, calling the embed text function incurs $1 per token charge to create the generated vector. But once that vector is stored, look at what happens when the user query vector arrives. Both vectors enter the vector inner product function. Notice the bold path. This operation incurs 0 token costs. It routes entirely through your standard warehouse compute. You are only paying for the seconds the warehouse is active, delivering rapid search results at a highly predictable, minimized cost. Let's establish the architectural best practices for writing high-performance retrieval queries. Novice developers often place the similarity function directly inside a where clause to filter out bad matches. This is an anti-pattern that forces the engine to calculate the math for every single row before filtering. Instead, you should place the vector inner product function in the select clause and assign it a column alias, such as similarity score. To perform a top K retrieval, you simply add an order by similarity score desk clause, followed by a limit 5. Furthermore, for maximum performance, you must combine semantic search with traditional pre-filtering. If a user is looking for a support ticket from the last 30 days, use a standard SQL where clause on the date column to instantly eliminate 90% of the table. By reducing the dataset first, you drastically lower the number of vector inner products the engine has to calculate. This flowchart outlines the golden path for vector retrieval. We begin with a massive vector table. Before any vector math occurs, we hit the pre-filter step using standard SQL where clauses. This eliminates the vast majority of irrelevant rows. Only the surviving records move to the compute-heavy step, calculate vector inner product. Once scored, the results flow into the order by clause to rank them from highest to lowest similarity, and finally, the limit node truncates the set. This tightly optimized payload becomes the perfect context window for your RAG applications. Let's apply this to a highly valuable, real-time enterprise use case, Retrieval Augmented Generation, or RAG, for an IT help desk. Imagine a user submits a new ticket saying, "User cannot install internal mobile app on their device." A standard keyword search might miss related tickets that used words like cell phone or software deployment. In our architecture, the application instantly embeds this new ticket into a vector. We then execute a SQL query using vector inner product to compare this new vector against thousands of historical, resolved tickets in our database. Because we are measuring semantic similarity, the engine correctly identifies past tickets dealing with MDM profiles and smartphone glitches, scoring them highest. We extract the top 3 results and seamlessly pass them to a generative LLM as context. The LLM synthesizes these past solutions and presents the IT agent with an immediate, highly accurate troubleshooting guide. Follow the data in this real-time RAG sequence. The help desk app receives the ticket, embeds it, and sends the query to the Snowflake database invoking vector inner product. The database performs the vector math, sorts the historical tickets by their similarity score, and returns the top 3 matches. Crucially, the app takes these historical answers and packages them alongside the original question, sending the payload to the Cortex LLM. The LLM reads the context and generates highly accurate fix instructions for the agent, closing the loop in seconds. To conclude, it's vital to know that this SQL capability is fully accessible to application developers using Python. By utilizing the Snowflake connector for Python, you can orchestrate these semantic searches directly from your backend services. You simply use the cursor execute method, passing your raw SQL string containing the vector inner product call. Snowflake processes the heavy lifting in the cloud and returns the similarity scores to your Python app as standard float tuples, ready for immediate use in application logic or further machine learning pipelines. To summarize, vector inner product is not just a math function, it is the high-speed, cost-effective engine that makes enterprise semantic search and retrieval-augmented generation possible. Thank you for joining this deep dive. Please like, subscribe, and visit quicktechie.com for premium certification prep, including extensive Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Our final diagram illustrates the Python integration architecture. Your Python application connects securely via the Snowflake connector, issuing a cur.execute command. This command triggers the vector inner product function. Notice that the intense mathematical calculation happens entirely on the Snowflake cloud compute layer, preserving your local application's memory. Snowflake quickly returns the calculated similarities as a float tuple back to your Python app. Keep building scalable AI, and see you at quicktechie.com.